Welcome back. This is our final lecture on this lecture series on nuclear fission reactors. In the previous lecture, we had briefly looked at nuclear fission reactors for research purposes. In this lecture, we will look at nuclear fission reactors for generating power. There are a lot of reactors that are available. Much of the material is sort of descriptive. So you can look at this book that will give you a description of the different kinds of reactors and to what extent they contribute to power, especially in the context of Indian energy scenario. We will just restrict our discussion to few things within the scope of this course. So the most common fuel is a solid uranium oxide fuel. It has, let's say, in this boiling water reactor, the amount of U-235 is about 2.5%. There are many components which are very similar in most of the reactors. This component is fairly universal in the sense that the eventual outcome is to generate electrical power. How is this done? It is done via steam being supplied to a turbine. So the efficiency of energy conversion depends upon what is called the Carnot efficiency. You must have looked at this in your thermodynamics classes. The Carnot efficiency depends upon the high temperature reservoir and the low temperature reservoir. So supposing if the low temperature reservoir is 298, why do you say this? Because the low temperature reservoir is usually a heat sink that is available to you, that is usually a water body or the atmosphere. That is at this temperature. So the essential control is on the high temperature reservoir. So if you have steam at higher the temperature of the steam available to you, the Carnot efficiency is greater. If you have a steam at only 373 Kelvin, your Carnot efficiency is very low. So the goal is to have rather high temperature steam, which does not corrode the turbine a lot. So a lot of engineering, metallurgical studies also go into the design of these systems. So in a boiling water reactor, these are the central nuclear reactor components. We have also looked at the components in a previous lecture. So there is a containment structure, which is just a structural material. There is a pressure vessel and cooling control rods and so on. So mainly water comes in, there is a thermal contact between water and this region of the reactor. It goes to boiling state and then gets distributed inside a turbine. In addition, there is a heat exchanger in this region. So in a pressurized heavy water reactor, one of the advantage of having high pressure is that the temperature at which water boils can be controlled. Okay, so the other aspects are rather similar compared to this aspect is rather similar. The main difference is here. And we have also discussed the advantage of using heavy water as opposed to light water. Okay, so please look up the previous lectures to understand the role of each of these components, the role of moderator, heavy water, and so on. Okay, so in a liquid metal fast breeder reactor, you do not use a moderator. Therefore, the neutrons available are at high kinetic energy, which has lesser cross section. We've discussed this again in a previous lecture. Um, but it has lesser complexities, but you have to use more enriched fuel. And the metal that is used as a coolant is the sodium metal. Okay. So sodium metal has a lot of advantage. It has much better uh, thermal conductivity compared to using water. And um, it can be melted at a lower temperature. So the other parts are fairly similar. Why use control rods and so on. So this part is also similar to all the power reactors. So finally, one of the most important aspect of nuclear reactor is its safety. Okay. So because nuclear energy is a very, very concentrated energy source and power source, that is its advantage and disadvantage. So the land area, the real estate needed to implement this reactor is very less. But if there's a failure, uh, the it is catastrophic. So the public acceptance is determined by the safety of the reactors. So it is a very critical factor. So one of the features that is troublesome in many other reactors, let's say if you look at the Bhopal uh, chemical reactor failure, one of the main issue was the snowball effect. What is the snowball effect? As the temperature increases, the rate of reaction increases, and if this heat is not taken out, that goes to increasing the temperature once more, which increases the rate of the reaction. So there's a cyclical change which keeps on increasing the rate of reaction. That's called the snowball effect. If you have taken a process control class, you might have heard this. Especially, this is discussed in the context of the failure in the Union Carbide reactor, uh, which gave rise to methyl isocyanide being emanated into the environment and led to a lot of death. Okay, so you do not want to have the snowball effect. So therefore, to have an inherently safe reactor, you want to have a negative temperature coefficient of power. What do you mean by that? As the temperature increases, the amount of power that is generated will decrease. So it automatically brings down the temperature. So how do you have a negative temperature coefficient of power uh, is an important topic in nuclear reactor research. We won't go into this detail, uh, but it is important to have this feature built into the system so that the nuclear reactor is inherently safe. So a sudden increase in power is counteracted by the inherent property of fuel, moderator, and coolant so that this is accomplished. There are also a lot of barriers. There's a fuel matrix. The matrix, other components sort of provide the initial barrier to emanations from the fuel. Then there is cladding, coolant, pressure vessel, building, and there is a containment area. Whenever there is a nuclear reactor, few kilometers uh, are called the containment zone, and it is typically away from highly dense areas. So many of the safety aspects that you uh, deal with in setting up a chemical reactor is also applicable to, in fact, it's applicable to a greater extent in a nuclear reactor setting. So there are these isolation zones and buffer zones between dense population and the nuclear reactor. But overall, the safety of nuclear reactors has been reasonably good given the large amount of power that is being generated. Of course, there have been few major accidents, Chernobyl and Fukushima and so on. And Long Island, there is also accident in the US. So these have to be studied as case studies. Uh, and a lot of lessons can be learned, and it has been learned. Uh, um, but the given that the nuclear reactors are very green in the sense that it does not generate CO2, the emphasis of nuclear reactors for power is going to increase. So, as mentioned in the first lecture of the series on nuclear reactors, the frontiers of implementation is in having more small modular reactors and micro reactors. These have better safety um, features, and the economies of scale will also kick in when you go into smaller reactors as opposed to the large conventional reactors, which there are a few hundred reactors worldwide in terms of large conventional reactors, but the future probably is in SMR nuclear reactors and micro reactors. Again, as mentioned earlier, International Atomic Energy Agency provides a lot of current and useful documents. If you're interested in this area, please go through the material presented in this website. Thank you. In the next lecture, we'll take up a new topic of nuclear separations. Thank you.